Okay, girls. Good evening, everyone. Okay, your lecture I am recording, no problem for future use. If you want, you can download the lecture and you can listen my class, no problem. Okay, inshallah. Today, now I will finish this introduction to trees, chapter section 10.1, chapter 10. This is the introduction to trees. Okay, so first coming to the tree, we have to discuss about what is a tree. See here, normally tree is a connected undirected graph. Connected undirected graph means there is no directions for the tree. Suppose see like this is the root of your tree, like this, and this is node of your tree, like this, like this, like this, like this. See, there is no directions. This is the tree. Okay, so but here with conditions, we have some conditions. No simple circuits. Circuits means like this, like this. No simple circuits, and no multiple edges. No multiple edges means like this, two nodes or three nodes, like this. No. Okay, then no loops. No loops means like this, covered, fully covered, like this, not present in the tree. Okay, so now you understand what is a tree, girls. Tree is a connected undirected graph. Yes, I am talking. I am talking. Are you not listening? You are not listening. You are not hearing my voice. Yes, dear, I am teaching the class now. You are not hearing my voice. Say yes or no, please. Okay, okay, thank you. Okay, now see here, this is the definition of tree. Okay, if I ask the definition of tree, you have to write, a tree is a connected undirected graph with no simple circuits, with no multiple edges, with no loops. Okay, no loops. Okay, now here coming to this one, an undirected graph is a tree if and only if there is a unique simple path between any two of vertices. See here, this is example. Yeah, this is one graph, and this is one graph, this is one graph, this is one graph. So among all these graphs, we have to find out which graph is a tree, which graph is not a tree. See here, the first one is a tree. So here you observe one thing, there is no loops. Okay, this one, and there is no simple circuits. Okay, and there is no like this one, what it is called, multiple edges. Okay, so no multiple edges. See, this is one edge, this is one edge, this is one edge, this is one edge. Okay, so like this, if you find like this, you will understand this is a tree. Okay, first one is a tree. And coming to the second one, here second one also no loops. See here, you will think maybe this is loop like that, but here there is no edge, right? If here edge means this is not a tree, but here there is no edge. So you can write like this, a c, and like after that f. For f you can write e, for e you can write b, like that you can make an order of a tree. Okay, so here also no simple circuits and no loops and no multiple edges, so you can consider this is also tree. And coming to this one, see this one, this is a not a tree, because here loops is there. See, this is one edge, this is one edge, this is one edge, this is one edge, this is one edge. For this edge no loop, but for this edge loop is there. See this one, like this, like this. So you can consider this is not. And coming to here, this is a separate, a and f is separate, there is no connecting edges, right? So there is no connecting edges. This is separate and this too is a separate. So you can consider this is also not a tree. Okay, so maybe this is very simple concept. If I ask the questions also, this is a tree or not tree, like that, if I ask the questions also, you can find out the solution and you can write the answer yes, yes, or no, no, like that. Okay, then coming to the next one, forest. What is the meaning of forest? So if any tree or if any graph, see here, graph, there are no simple circuits, but the graph is not connected. Okay, so inside the tree, there is no simple circuits, but graph is not connected together to each of the connected components in a tree. So this type of collections is called as a forest. This type of collections is called as a forest. See example they gave like this. This is a tree. So here also this is not a loop. You can consider maybe this is a loop, but this is not a loop. You can write this diagram like here you can see A, B, C, D, E, F. Okay, so you can write this is like a tree, like undirected tree. You can consider maybe E is a root, like that you can consider. So first for E, what are the children's is there here? D, F and B. This is B, right? D, F and B. You can write like this. This is D, okay, and this is B, okay, and this is F. You can write like this. Okay, after that for D, you can check for D, is there any links, is there any edges? No. Now you can check for B. Yes, for B it is there. So you can write like this, A. Okay, after that you can check C. Where is F here? For F any link is there? Yes, you can write C. Okay, see this one, this is a tree. Okay, if I ask like this, draw the given graph into in the form of tree, means you can write like this one. Okay, if the tree is like this means we can call it as a forest. Okay, then coming to the next one, rooted tree. Yes, rooted tree. Rooted tree means you can consider any of one vertex as a root. This is called as a vertex. Okay, you can consider any tree, any vertex is a root. So by using that root you can describe the children's like left, right and like that you can describe the tree. So this is called as an example of rooted tree. Okay, then see here example, you can consider here T is a, sorry, B is a root. This is a B, right? So if I give, this is graph, right? So if I give like this, this is graph. You can write this graph in the form of rooted tree. Here you can consider B is a root. So B is the root. First describe for B what are the edges are connected. First E, okay, then D, okay, then F, okay. After that for D there is one edge, that is called A, and for F there is one edge, that is called C. So after that you can make like a tree. Okay, so this is example of rooted tree. Then coming to yeah, this is also another example, different rooted tree. You can consider C is a tree, a root, and also you can consider F is a root, and also you can consider E is a root. Anything you can consider a root and make it as a tree. Okay, this is another example with different rooted trees. Okay, then coming to the tree terminology. Yeah, terminology means history. What is the history of tree? Okay, normally we can consider tree, we can mention tree is like a T, capital T, okay, other than the root. Okay, suppose this is we can consider this is the root, and we can say this root is a parent. We can say this root is a parent. After that there is some unique vertex called like U. Okay, like any another thing like A. This is called as a children. Okay, children. When U is the parent of V, V is called the children of U. That means here you can see, okay, you can consider this is a U, okay, and this is a V. Okay, this is a child and this is a parent. So, and if any other people is there like this, A and B, like this, we can say this is siblings, like a sister, brother, like that, we can say it is a siblings. Okay, then example for the tree, see here, yeah, see here example. Okay, see these three siblings, we can say these three siblings, and we can say these three siblings like sister, brother, like that. Two siblings, okay, and these two siblings. Okay, so this is a parent, grandparent, okay, grandparent of these and these children, and this is a parent of these children. Like that we can consider it's a tree terminology. Okay, see here example, yeah, this is a siblings, this is siblings, this is siblings, this is siblings. Okay, then ancestors of vertex other than the root or the vertices in the graph, in the path from the root to this vertex, excluding the vertex itself and including the root. Okay, so we can see examples of what are the ancestors and what are the descendants of vertex. Okay, see in this example you will understand. Yeah, see this one, ancestors of K. Okay, ancestors of K, that means four parents of K. So who is the father of K? F here. Who is the father of F? D here. Who is the father of D here? D. A. Okay, so now we can say K ancestor is A. That means grandparent. Okay, so see here this one. Yeah, descendants means, okay, that is ancestors means parents, their parents, like that. Okay, now coming to the descendants of D, we can find who is the descendants of B. That means relations of B. Okay, that means grandchildren of D. Okay, first C we can consider here, D is a father. Okay, D has three children, these three children D. Okay, again F has K and H has two children. We can say these all, yeah, this relation. Okay, and we can say this relation. Okay, like that. Descendants means parent, their grandchildren and their relation. Okay, then a vertex with no children is called a leaf. Like this, suppose it is a vertex. Okay, this has two childrens, A and B, for example. Okay, suppose this don't have any childrens, this we can say leaves, because there is no childrens. If like this means we can say left children and right children. Okay, and another vertices with children are called internal vertices. Okay, then yeah, see here, these are the leaves because no children for this. This also leaves, no children for this. This also leaf, this also leaf, this also leaves because no children's, right? That's why we can say leaves. And internal vertices. Internal vertices means, see, this is main parent and this is also parent. 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 Now you will understand, girls, if which root, which vertex has a children, that we can say internal vertices. Which root, that is which vertex don't have children, that we can say as a leaf. Okay, then subtree. What is a subtree? Suppose if A is a vertex in the tree, the subtree with A is root as subgraph, the tree consisting of A and its descendants and all edges incident to these descendants. See, now we can coming to the example, yeah, see here, this is a parent, okay, main parent, big parent, and this is a another parent. We can say subtree at B. Okay, that means only the relation of B. This is subtree of B. And we can say here subtree of D. Okay, only the relation of D. Okay, like that we can say. Now suppose here consider another thing. Yeah, suppose consider another thing. What is the subtree of H? Only this. This is the subtree of H, because H, L, M, this is one tree, right? Subtree of H is L and M. Okay, like that we can write what are the subtrees of the given parents, the given roots. Okay, now coming to the rooted tree, we can say it is a M array tree if every internal vertex has no more than M children. Okay, suppose each and every root has a children in the given tree, that tree we can say it is as a rooted tree, and also we can say it is a M array tree. Okay, and if any another tree, okay, if that tree full M array tree, that means each and every vertex present in the tree has exactly some children, 2 children, 3 children, like that. That is called as a full tree. Okay, another tree, binary tree. What is a binary tree? That means in given tree each vertex has two, see this one, 2 children, minimum 2 children. This tree is called as a binary tree. Okay, see here, consider example. What is the arity of the tree? Okay, in this a full M array tree, this is a 2 array or binary tree. That means each parent has 2 children, for this 2 children, and for this 2 children, and for this 2 children. So why we can say this is a full binary tree, because each parent has 2 children, right? So that's why we can say this tree is a binary tree. Okay, and here see this one, we can say full 3 array tree. That means each parent has 3 children, this 3. Okay, and this parent has 3 children, and this parent has 3 children, and this parent has 3 children. That means each and every root has a 3 children. We can say this is called as a full 3 array tree, exactly 3 children, because that's why we can say full 3 array tree. Okay, then coming to 5 array tree. That means each parent has 5 children. 1, 2, 3, 4, 5. Okay, this 5 children. And for this parent, we have 5 children. 1, 2, 3, 4, 5. There's 5 children. See, like that. Depending on the children's, we can consider this is a which type of tree. Okay. And another example here, say this one, same thing. Some internal nodes has a 2 children. See, this node has a 2 children, and this node has a 2 children, but this 2 nodes has three children, right? Okay, this is different. This one 3 children, okay, and this one 2 children. That means we can say it is not a full 3 array tree, but it has only some roots has only 2 children, some roots has 3 children, like that. So we can say this is not full M array tree. Okay, ordered rooted tree. Okay, so see here we have some definitions here: ordered rooted tree, ordered binary tree, and subtree, left subtree, and right subtree. Okay, ordered rooted tree. Ordered rooted tree means, see here, the children of each internal vertex are ordered. That means for each and every root has minimum childrens, maybe 2, maybe 3, like that. Okay, ordered binary tree. Ordered binary tree means, see here, this is a root, and this root has 2 children, and this is a root, this root has 2 children, and this is a another 2 children. That means each and every root has 2 children, left child and right child. That tree we can say it is a ordered binary tree. Okay. Then coming to the subtree, rooted at the left child of the vertex is called left tree. We can say this is a left tree, and we can say this is a right tree. Okay, depending on the left children, depending on the right children, we can say this is the left tree and this is the right side tree, right subtree. Okay, and consider an example. This is a parent, and we can say this is the left subtree. Okay, left subtree, and we can say this is a right subtree, right subtree. We can say this is a right subtree. Okay, yeah, right child of D, right child of D. Who is the right child of D? G. This is a what it is called, left subtree. Okay, but the right child of D is G. And we can consider, yeah, left subtree of C. Yeah, this is the root. If you consider, this is the root, this is the left tree, and this is the right tree. Okay, like this. Yeah, see, this is the right tree. And then the level of vertex. So how can we find out the level of vertex? That means length of the unique path from the root to this vertex. So what is the level of the root? 0. We can say that the height of the rooted tree is the maximum of the levels of the vertices. Okay, consider the example. How can we mention that? What is the level of vertex and what is the height of vertex? Yeah, see this one. This is 3 levels. Okay, so this we can consider this is levels, and the height means how many levels. Okay, so this is the first level, this is the first level, and this is the second level, and this is the third level. So by considering these, we can say the height of this tree is 3. Okay, and how many levels here? 3 levels. We have 3 levels. Okay, then coming to the some properties of the trees. So each and every trees has to follow some properties. So first, what are the properties? Here we can see a tree with n vertices has n minus 1. That is a property. Suppose here maybe 4 vertices is there, so 4 minus 1 edges will be there. That means 3, maybe left children, right children, center children, like that. Okay, and then a full M array tree with I internal vertex contains n is equal to mi plus 1 vertices. Okay, and a rooted binary M tree of the height h is called as a balanced if all levels are at levels height are h minus 1. Okay, if the tree contains the balanced levels, that we can say it is a balanced tree. Okay, then see here, consider an example. Is this tree, the given tree, is balanced or not? Yes, we can say this is balanced, right? 1 level, 2 level, 3 level, 4 level. The height of the tree is 4. Okay, yeah, write it down, the answer also, girls. The height of the tree is 4 and this tree is balanced, because each root has two children. So we can say this tree is balanced tree. Okay, the height of the tree is 4. Then consider another example. Yeah, is this tree is balanced? No, not balanced. Okay, we can say it is a tree, but height of this tree is 4. Same like that, 1 2 3 4 4. Okay, but the tree is not complete tree. It is a balanced tree but not complete tree. Okay, then yeah, here is this tree is balanced. Yes, 1 2 3. Here 3 levels, 1 2 3 levels. The height of the tree is 3 and the tree is balanced. Okay, then coming to that, there are at most m power h leaves in the M array tree of height. If M array tree with L levels is full and it is balanced, we can calculate the height of the tree is like this. H is equals to what is this, VGM. Okay, I will see this example, then I will write here the clear formula, girls. This is not clear. Okay, I will write after that. Wait a minute, I will write the tree. 1 minute. Yeah, I will write this one. H is equals to, copy. Yeah, H is equals to log, I think you have, right? Log M L. Okay, so this is the formula for calculating the height of the tree. Okay, then yeah, this is homework exercises. You can solve in the home these exercises. Okay, then coming to the application of trees. Okay, here we will discuss some application of trees. Okay, first application of trees. We have different types of trees, right? Binary search tree, decision tree, prefix code trees, and gaming trees. We have 4 different types of applications of trees. First, coming to the binary search tree. Full and complete binary trees. So normally everyone can remember that binary means 0 and 1. So if the any parent has degree 2, that means, see here, if any parent has exactly 2 children, we can say that that tree is called as a full binary tree. And the complete binary tree means it is a full binary tree which all leaves has the same depth. That means in the tree, inside the tree, each and every node has a 2 children. That tree we can say it is as a complete binary tree. Okay, then coming to the next one, nearly complete binary tree. Nearly complete binary tree means each node has a 2 children, but maybe left side or right side will not complete the tree. So that it is that tree can called as a nearly complete binary tree. Okay, see, this is examples. This is a full binary tree. Okay, and this is a complete binary tree. You can understand the difference between full binary tree and complete binary tree. Complete binary tree means however the nodes, how many nodes is present inside the tree, all nodes has a 2 children. See, for this, this and this, for this, this and this, for this and this is also binary tree, full binary tree, but here it is not complete. So till here it is stopped. So but here it is stopped, but each node has 2 children. See, this is 2 children, this is 2 children, but this 2 children, like this, but not complete. Okay, this is the difference between the full binary tree and complete binary tree. Okay, now coming to the binary tree, some points related to the binary tree. Okay, what is the smallest height possible in the binary tree of 2 power n minus 1 nodes? Okay, so this is the question actually, and this is the solution. The smallest height is possible in binary tree of 2 power n minus 1 is n minus 1 nodes. If the binary tree contains the n minus 1 nodes, this smallest height will be there for the binary tree. So see here, they gave one small example. One tree contains the 31 nodes. 31 nodes. 31 nodes has means 2 power 5 minus 1. Okay, so 2 power 5 means what? 2 multiply by 2 multiply by 2 multiply by, like that, 30. Okay, sorry, 32 minus 1, that means 31. So here 31 nodes. So we can consider n is a 5, that means this one, n is a 5, and we can calculate the height is n minus 1, that means 4. So if the 31 nodes of the tree means like this, 1 2 3 4 5 6 7, 8, 9, 10, like that. So height is 4, like this, 1, 2, 3, 4. So like this you can consider and draw the binary tree. See here example, same thing. This is another example. Okay, yeah. So here height is true, the tree height is true. The nodes are 7 nodes, 1, 2, 3, 4, 5, 6, 7. So the nodes are 7. Height is true. See, 1, 2. This is 1 and this is 2. Consider the height of the tree is 2. And number of leaves 4. This one. The number of leaves is 4. 1, 2, 3, 4. So you can write the tree, you can draw the tree like this, depending on the nodes and depending on the leaf nodes. Okay, and see this one, the height of the tree is 3. 1, 2, 3. Okay, this one. Then this is another example. Height of the tree is 4. 1, 2, 3 and 4. The height of the tree is 4. The number of leaves is 16. This is leaves. This is leaves. Okay. Then, yeah, this is not there on it. Okay, these are all examples of explaining the trees and all. And this is the difference between the mathematics, physics example. A binary search tree example. Okay. And binary search trees. Okay, this is example. You can search these nodes like this. Enable vertices. Yeah, and this is a decision trees. Greater than b means like this, less than b means like this. Decision tree examples. Okay.